Hi everyone, I'm Jack. Welcome to my talk. It's Race to Auth, How I Stumble Upon Race Conditions. I want to kick off with a bit of a disclaimer. I am by no means an expert. I like to throw things at a wall. I hope something sticks. This talk doesn't come with a warranty and is in no way endorsed by Microsoft or Citadel. Bit about me, who am I? I'm a security consultant at ZX Security. Cracker of hashes, race of conditions, and doer of dumb things. In the last year, I have been part of or found 7 CVEs that have impacted Microsoft, Citadel, precisely spectrum analysis, and a couple that are currently in disclosure. And I'm a first-time speaker. So a bit of an outline of what I want to talk about today. What is a race condition in a web application? Exploiting a race condition in a web application. Potentially defending against a race condition. And maybe some demos of some POCs if they work. So let's kick off. What is a race condition? A race condition is an undesirable situation which occurs when a system attempts to conduct 2 or more operations at the same time. They can occur in web applications when requests are processed concurrently, leading to multiple threads trying to interact with the same data at the same time. But is this not the point of a web application to do multiple things at the same time? You'd think, and that is the case, but what happens if one user is the one that uses them concurrently? Like a login form. Submitting MFA codes, applying discount vouchers, or requesting refunds. All of these should have limits in place and be accounted for, right? So brute force protection on the login form, or valid time windows for MFA codes, vouchers that should only be used once per transaction, or 1 refund per purchase. These limits can cause race conditions if not implemented correctly, specifically known as limit overruns. But I ask, why can this introduce a race condition? Well, as an application begins to process a request, it needs to enter a state that conducts the appropriate checks. Some may call them substates. In the example above, we have 2 requests happening concurrently, where we submit a discount code, which is based on the code being checked if it's already been used. We're going to apply the discount, and then we're going to set the code in the database as already used as true, and then update it. But introducing this can introduce a race window where the previous check, request number 2, relies on the same thing that's being checked. In operating system programming, I believe this is called critical section programming. So this can be applied to many areas, such as submitting 1 authentication request, submitting more than 1 MFA code, or applying the same discount voucher, or requesting a refund twice. But rather than talking about it, let's use an example. So let's use Microsoft. I was testing a web application. It was written in ASP.NET, and it had a login form. This login form had a lockout set to a maximum of 3 attempts, and it was using Microsoft's off-the-shelf identity manager. So I thought to myself, what happens if I attempt to log in concurrently? And well, that's what I did. So what you're seeing here is the result of 100 authentication attempts being sent extremely fast, with the majority of them failing due to the password being incorrect. But I'd like to note that the account locked out on request 78. So when this lockout should have happened at 3, right? So the important thing to note with the requests after 78 is that these are still valid requests. They still got processed, and the account is not locked because all of these are happening concurrently. We have successfully bypassed that lockout threshold of 3 and got 99 in. This is bad for Auth, and Microsoft, they agreed. Checking the logs revealed that multiple threads attempted to update the database at the same time, with error messages such as DB update concurrency exception littered throughout it, with helpful links in that to go, hey, how to deal with a race condition. But rather than seeing the result of a log, why don't I show you the POC in action? So I want to explain what we're going to walk you through a couple of screenshots here. First off, this is a web app that we spun up using Microsoft's vulnerable ASP.NET Sign-In Manager. It also used their default templates. We're going to send a login request to that platform, and we're going to try and intercept all of the cookies and tokens that are associated to it, as you can see in the request here. And I'm going to pop them into my proof of concept here. I want to note the top parameter requests. I'm going to try and send 100 of them. Let's give it a hoon. Brilliant. So, as you can see, all of these requests were sent concurrently. And request number 55 passed the authentication, with 99 of them failing and no lockouts occurring. Once again, I want to stress the lockout was 3. Just as a visual aid for visual learners, I want to try and explain what we saw here. So we submitted an authentication request. Now, I've offset request 2 to kind of demonstrate what's going on here. And we've entered the race window, where it checks if the account lockout is false. And since both of these requests are happening at the same time, both of them will check that value, and it will be true. And then it will check if the password is incorrect and increment that value. Now, if this is happening hundreds of times, we're now racing that update. So, okay, this was interesting. So if Microsoft made this mistake, I started asking, did anyone else? And I decided to look around, and I came across a platform which is an identity manager provider called Citadel. Citadel is an identity infrastructure provider which provides authentication management for a range of applications, such as hosted login, passwordless authentication, multi-factor authentication, and single sign-on. A great way of thinking of it is an on-prem Okta. So once again, let's have a hoon. Pulled down the Docker image, deployed it over a network, and configured the login form. And I want to stress, I set the lockout attempt to 3 again. And it happened once again. Once again, you are seeing the log output of my proof of concept, which can see multiple requests were happening concurrently. The account lockout happened at request number 2, and the rest just continued going. We have successfully bypassed that lockout threshold again, and once again, this was bad for Auth, and Citadel also agreed. Want to see another POC though? So this is the admin panel, and this is great because I can set the maximum attempts, and in the top right-hand corner, you can see that policy was set successfully. Great. Once again, I'm going to intercept that those requests, and I just want the tokens, I want the cookies, and I want to pass it to my POC. You'll see at the bottom there, number of requests, I'm going to send 20. Let's see how it went. Oh, brilliant. So once again, you are seeing multiple login fails and then a login success. Once again, the lockout was 3. There's 19 failures there. And they actually had a pretty similar race window where they checked the account lockout, relied on that value, and then checked the password if it was correct or incorrect, and then it incremented that value. So we're racing that update there. Why did this happen though? As mentioned, the first application was using ASP.NET's default sign-in manager, which is part of Microsoft's identity framework. It provides built-in functionality for managing user identities, including registration, authentication, authorization, but it also contains an important flag called lockout on failure. And when that is used, it enables a bunch of checks to lock out the account. However, if racing begins, the outcome of this check, once it's enabled, doesn't update fast enough. In the case of Citadel, they were also subject to the same race condition, specifically in their password lockout policy. The same thing happened. Now, I want to talk about potentially exploiting a race condition, because I've shown you all of this, but let's take a look at some of the attacks we can do. You've got over HTTP 1.0, 1.1, you've got last byte sync attacks. You've also got single packet attacks over HTTP 2, and my favorite, the spray and pray. So I'm going to start with the last byte sync. This method or technique used over HTTP 1 is where multiple requests are sent concurrently. So I'm going to use this as a visual aid here, where you can see the trains coming into the server are the requests. But you'll notice the last carriage is held back. Consider that the last packet, and you hold that back for a short amount of time, and then send it to complete the requests. This way, you can minimize the impact of network congestion, latency, jitter, and improving the chances that these requests are processed simultaneously or very close together. But in comes HTTP 2, and I'm going to give two main points I want to highlight, very high-level overview of them, is that in HTTP 2, one TCP connection, you can have multiple requests. This request does not need to be fully completed before starting the next request. So in comes the single packet attack, which was demonstrated by James Kettle in his talk, Smashing the State Machine, at DEF CON 31. Because HTTP 2 allows for multiple HTTP requests to be sent over one connection concurrently, we can combine that with the last byte attack. By combining them, we can have multiple requests come in, and we can finish them all in one packet as the last byte. This means more requests are arriving at the same time from the application's perspective, allowing 20 to 30 requests to be completed in one TCP packet, according to James Kettle. Now, for the visualization purpose, each box represents a TCP packet, and each train represents a request. However, you have all of these fancy techniques. But remember how I said I like to do dumb things? Yeah. My favorite approach is the spray and pray, where I try and send fully completed requests as fast as possible. It's a really dumb approach, but it works pretty well. There is nothing special or surprising about that. Now, if we wanted to look into tooling, you've got Burp Suite, where they've just updated the repeater functionality to do the single packet attack. By having groups, you can make as many requests as possible, click down arrow, and away you go. My favorite thing, though, is Golang for its native concurrency. It allows me to do things programmatically by chucking the word go in front of it. Now, I've talked about attacking. Why don't we take a look at defending against a race condition? I'm not an expert in this field, but I want to take away a few key ideas. Finding a way to synchronize or control the order of operations. And to do that, we need to understand where race conditions could exist. Conduct a risk assessment of your code. Do a code review. But in that, consider, does the race condition have a substantial business impact on your authentication, your MFA, your payments, or any security boundaries? Do they have limits in place, and could they be overrun? And when you're doing this, consider what defensive mechanisms exist. Can you offload this problem to a library? Does the language your app is built in have defensive mechanisms, such as locking? I believe Python has threading.lock, Go has sync.mutex. Can you use database transactions, atomic database transactions, like a select for update? But it's important to note that these mechanisms may not work in the context of your application. Everything is different and unique. But also, don't trust that race conditions have been checked for. I have found this in quite a few places. I'm currently in disclosure with a couple of other vendors that have the exact same issue of me just sending packets. Concurrency issues are easy to write by default. It is really hard to program something asynchronously. The amount of times I had concurrency issues trying to exploit a concurrency issue. It happens, but Go is nice. It tells me you're racing yourself. And as things become more distributed, I feel like this will become more apparent. HTTP 2 and 3 have native multiplexing. Okay, but I've talked about all of this. Where can I start looking for these bugs? Anywhere that has a limit in place, really. See if you can race it. Authentication libraries, authentication platforms, or IDPs, they're great examples. But also, I'm saying this, do it ethically and responsibly. Make sure they have a disclosure program. But in summary, we have looked at what a race condition is. We have demonstrated 2 limit overruns and looked at potential defensive mechanisms in place and demonstrated 2 race condition POCs. Also, I can't stress this enough. Do try dumb things. It works. It's surprising, and it's kind of rewarding. I just quickly want to acknowledge a few people. TC and Ethan, they are both key contributors to the first race condition I discovered. Come talk to them too. They're in the front row. I'm pointing them out. Carrot, he has listened to multiple, and I cannot stress this enough, multiple revisions of this talk. My colleagues, they have been nothing but supportive. And Kevin. I made the mistake of mentioning I'd never spoken at a con before, and well, here I am. And the Christchurch Con crew, thanks for running this amazing con. It's actually been a blast. I've really enjoyed it. Finally, all my proof of concepts will be available on GitHub in the coming days and uploaded to the appropriate blogs on the ZX security websites. Some references, and feel free to come talk to me after the con. Also TC and Ethan. I'm going to throw them under the bus. Come talk to them too. Thanks, everyone.
I am a super genius.